All right, so this video is your review for the second exam. Of course, the exam is going to be the same format as the first exam was, same way of doing things. Probably a similar amount of questions, so no difference in the type of exam, but of course, the topics is of major concern. This test will be on all the topics we've covered since the first exam. So it's not cumulative. It's only on the stuff we've done since the first exam. And really, that's only two big topics. The first is work. And for work, we had, first of all, the equation work is force times distance. And we discussed how when we talk about force times distance here, what we mean is how much of the force is in the direction of motion, so like the parallel force. So basically, given a problem, you figure out which way will the item move, then figure out all the forces that are in that direction, add them all up, multiply by how far the object moves, and that gives you the total work. Of course, along with the work, we could also use the work energy theorem, which says that if you know how much work is done on an object, then you know how much the kinetic energy of the object has changed. Kinetic energy, kinetic energy, of course, being 1/2 mv squared. So basically, by applying work, you will change the velocity. It means the same thing as the Newton's second law, F equals ma. If you do a force, you get an acceleration. Only here, it's kind of a different form. Work changes the energy, changes the motion, the velocity. And so we did a bunch of examples, given a bunch of forces acting on the object, what's the total work done, and how fast will the object be moving at this distance, and so forth. So that was the stuff about work. The next was conservation of energy. And conservation of energy basically had one big topic, and it says that the total energy of a system must remain constant. So if you know all the energy in a particular system, as long as the system's closed off to surroundings, then no matter what happens, as time progresses, that same amount of energy will always be there. Now, some of the energy may go to kinetic, it may change to potential, whatever. But if you add all the energies together, you get the same number. And so the equation for that says kinetic energy initial plus potential energy initial is kinetic energy final plus potential energy final. And so we saw a bunch of examples here, given that there's two different types of potential energy. First type was gravitational, and that's a MGH. That's, a ball or a block slides down a hill, or it goes up a hill, whatever. You change or you lift a block from the bottom to the top. You've changed the potential energy because the height of the object has changed. The other type we needed to know was for springs. When you compress a spring or stretch a spring, you give energy to the system. The spring stores the energy, and it stores it using the equation 1/2 kx squared, where k, of course, is the spring constant, and x is how much you've stretched or compressed the spring. So these are two big topics. I've had to cut down a little bit on what we would normally do just for time constraints. We're running out of time in this semester. And so I wasn't able to get to quite as much as I wanted. One thing to note is if we were to move a little forward with conservation of energy, and I believe I mentioned this in one of the videos, we would also talk about how does friction come into play? What if our hill is a grassy hill? Obviously, the block won't necessarily keep sliding forever down a hill. If there's a lot of grass, it may get stuck. And so there's a modification to this equation which allows you to place work into this conservation equation. Unfortunately, like I said, just time constraints didn't let us get to it. But you should know that it exists. And so if you're looking in your textbooks or you're looking at other YouTube videos or whatever with people solving conservation of energy problems, you may see people add on plus W here or plus W here and stuff like that. But for us, for our class, we don't have to worry about it. So don't concern yourself with problems that include work done by friction or things in this. It's just what we've done in class, just the practice problems we've been doing. So I figured, of course, I'd give a few examples of the types of problems you might see on this test, just so you get a feel for what the questions look like. But of course, as is always the case, the best way to get comfortable with the material and to see the types of questions that will be on this test is to go on Canvas, get the practice problems that are posted, and just work them out over and over and over again. And I promise you, I don't have a good enough imagination to come up with thousands of different types of questions. I've come up with some questions for the homework or some questions for the practice problems. Those are the types you're going to see. So practice them. Don't just copy them. Understand why certain terms are used, why this number is this, and so forth. Be able to do it from a blank sheet of paper. And don't just memorize what the numbers are, because I'm probably going to change the numbers on the test. So, you know, if in the practice problem, it's a 5 kilogram block sliding down a 10-meter hill, but in the real test, it's a 10 kilogram block sliding down a 20-meter hill, well, you're going to get the question wrong if you use the wrong numbers. Yeah, you might be solving the problem the correct way, but if all you did was memorize the numbers from your homework and try to apply them to the test, I'm going to mark off. Because it tells me you don't understand how to solve the problem. All you know how to do is memorize. I don't want you to memorize. I want you to be able to look at the problem, say, I've seen this type of problem before. I remember the technique. Let me use this technique and solve the problem out and get the answer. All right, so example 1, this will be a work problem, work energy type problem. Let's say we have a block on a nice horizontal table. Block has a mass of 10 kilograms, and I push with 3 forces, 5 newtons, 20 newtons, 40 newtons. And my block slides to the right a distance of 30 meters. If this force is at an angle of 30 degrees, I'd like to find the total work done and the speed of the block at the 30-meter mark. Okay, so 2 parts. Part A, what's the total work done by my forces? And part B, how fast will this block be moving when it reaches the 30-meter mark? Okay, so part A, finding the total work. First thing I do is I say, in which direction will this block move? Because, of course, if I want to calculate work, I need to know the force in the correct direction, so I need to know the direction. Well, obviously, I'm told this block is going to move horizontally to the right, so it's going to be an x-directional distance. All that means is all I care about are x directional forces. So all the components of the forces that are in the x direction, that's what I want. Well, let's look at the forces I have. Here's force 1, force 2, and force 3. Force 1, does that have an x component? Yes. F1 has an x component of 40 to the right. The whole thing is in the x direction, so that's good. F2, does that have an x component? No. F2 is vertical. It's a y directional force, so it's all in the y direction. None of it's in the x direction, so that's 0. F3, does he have an x component? Yes, he has an x component because he's at an angle. So what's his x component? Well, of course, we can do our little triangle thing, which we've been doing this whole time, and we get 20 cosine 30. And so we would get our little calculator out. We do 20 cosine 30, and we get 17.32. All right. So those are all the forces. Of course, there's also gravity, mg. But notice gravity is a y-directional force always, and so I don't care about gravity for this problem. I'm looking in the x direction, gravity is y direction, so I just skip it. All right, so I want to find the total work, and I know that's the total force times the distance. Well, let's see. I could do it like that, or I could say the total work is going to be the work due to force 1 plus the work due to force 2 plus the work due to force 3. Let's try it like that. The work due to force 1. All right, so it's F times X. F1, that's 40 to the right. X goes 30 to the right, so he's positive, so I leave him positive. Next, work 2. I need F2, which is 0, times X, which is 30. And in work 3, F is 17.32, times the distance is 30. But notice for force 3, the distance is to the right, but my force is to the left. So this guy is going to be negative. So this work is a negative work. Okay. Again, he's negative because the force and the distance are opposite to each other. So there's my little equation. Work 1, work 2, work 3, add all the works together, I get a total work. So what do I get? 0, 0, 1, 2 for him, plus 0 for him. And then 17.32 times 30 will give me 519.61. Again, this is negative. Let me erase that really quick. He's a negative work. And so I add this together, 1200 minus that gives me 680.4 joules. I now know the total work. Of course, the other way I could have done it was I could have said, well, the force, so let's see, I've got 40 to the right, plus 0, plus minus, of course, because he's to the left, minus 17.32. Does the total force times the total distance of 30, and I'd get the same number. It just depends on how you like thinking about it. I've found a lot of people like thinking about the total work. You just add the individual works together. It makes the numbers easy. And it makes knowing when do you say positive, when do you say negative okay. But if you like adding all the forces together first and then multiplying by the distance, you could do that too. You just have to be careful about your negatives. Anyway, part A is done. I now know the total work. What about part B? Part B, I want to know the final velocity. Or I want to know the speed. What's the velocity of the block at the 30-meter mark? Well, of course, I'm using work energy theorem. Work is equal to change in kinetic. Change in kinetic, that means kinetic energy final minus kinetic energy initial. Now notice this problem didn't tell me I was moving at the beginning. So I can assume my initial kinetic energy is 0. So kinetic energy initial is 0 for this particular problem. So all I have is kinetic final. So my equation becomes work equals 1/2 m v final squared. There we go. That's what I want to solve. And what I want to solve for, V final. I want to know what's the velocity of my block. So I can plug my numbers in. Work, I just calculated the work. It's 680.4 equals 1/2. The mass of my block is 10 kilograms times V squared. So V, that's going to be the square root of 680.4 divided by 1/2 of 10 is 5. So I get out my calculator and I get 11.67 meters per second. So that's not so bad. Work energy theorem type problems. First of all, calculating the work, the most critical thing. Make sure the force and the distance are in the same direction. So you may have to do components. You may not have to do components. It depends on the system. Here we had to do components for one of the forces because it was at an angle. But anyway, you figure out which way will the block move, X or Y, whatever it is. And whatever it happens to be, get all the forces in that direction. From there, calculate your total work, and now you have the work. Once you have that, you use work energy theorem to calculate the velocity. So that's a typical, nice work energy theorem type problem. What about a conservation of energy? Let's look at an example of that. Well, let's do this one. Let's say we have a wall with a spring, and there's a block attached to the spring whose mass is 5 kilograms. All right, first thing you do is you compress this spring by 2 meters. So you push the block up against the spring, compressing it by 2 meters, and then you're going to let it go. And what's going to happen is going to slide around the ground, go up a little hill onto a ledge. If this ledge is 3 meters high, I'd like to know how fast will the block be moving at the top. Now I need to give you one thing. I need to tell you that the spring constant of this spring is 500 newtons per meter. So that's how stiff the spring is. So that's our little system. We have a little spring. Block is attached to the spring. We push the spring, compressing it by 2 meters, then we let go. It shoots the block slides across the ground, goes up a hill. The hill is 3 meters high. Once it gets to the top of the hill, it just keeps sliding along. I want to know how fast will the block be sliding at the top of this hill. All right, well, this is conservation of energy. So I'm going to say kinetic initial plus potential initial is kinetic final plus potential final. So I need to see what are my initial states and what are my final states. Okay, initial state's over here. I've compressed the spring. Final state, I'm up here sliding along the top of the hill. So, initial state, my block, I've compressed it against the spring and I'm holding it there ready to let it go. At that point, I ask myself these questions. First, am I moving yet? Obviously, I'm not moving because I'm compressed against the spring, being held there. I haven't been released yet, so no kinetic energy. Potential energy. First question, am I some distance above the ground? No, I'm still at the ground. I'm just compressing a spring, but I'm not up on a hill or anything, so no potentially due to gravity. Third question, am I compressing a spring yet? Yes, in the initial state, I am compressing a spring, so 1/2 kx squared. All right, so that's the initial state done. Now forget about him. I now look at the final state. Final state. I've slid across the ground, slid up this hill. I'm now at the top of the hill sliding along. At that point, am I moving? Yeah, I assume I'm moving. I have no reason to think I'm not, so 1/2 mv squared. I would not be moving if the question said, how high will I rise? You know, if I assume this hill can go infinitely high, and I want to see just how high will I go, then in that case I would say the final kinetic energy has to be 0, because if I'm as high as I can go, then I must have stopped moving. If I'm still moving, I'm still going up. But here, I'm not told that. Here, I'm told I go up a certain distance, so I have to assume I can still be moving there. So 1/2 mv squared is there. Second question, am I some distance above the ground? Yes, I'm 3 meters above the ground, so there's an mgh. Last question, in the final position, is there some spring being compressed anymore? No, I've already let go of the spring. It's been released. There's nothing to do with the spring over on this side, so no 1/2 kf squared over there. So there we go. Here's my equation. All I have to do, of course, is plug numbers in. And usually what I like to do before I plug the numbers in is see, is there anything I can cancel? Well, let's look. There's a 1/2 here. There's a 1/2 here. But there's no 1/2 on the last term. So I can't cancel the 1/2s because it would have to be on every term. What else? There's an m on this term. There's an m on this term. But there's no m over here. So I can't cancel the m's. In fact, there's nothing that's the same on all 3 terms. So there's nothing I could cancel. I have to leave everything. All right, that's fine. 1/2 k. K is 500. X, I've compressed the spring 2 meters squared, remember the squares, equals 1/2. The mass is 5. V squared is what I'm looking for. How fast am I moving at the top? Plus m, 5, times g, 9.8, times the height in the final position is 3. All right, so let's see. Remember, I want to solve this for v. So what do I have? 1/2 of 500 times 2 squared. 2 squared is 4, divided by 2 is 2. 2 times 500 is 1,000. What about this term over here? This 5 times 9.8 times 3. That's 147. I want to bring it to the other side, so I subtract it over. Minus 147 equals 1/2 times 5 times v squared. I want to keep v squared here and get rid of everything else, so I have 1,000 minus 147 divided by 1/2 of 5, and I have to take the square root. That'll give me my v. So what is that? 1,000 minus 147 is 853, divided by 0.5, divided by 5, and take the square root. And I get v is 18.47 meters per second. So that's how fast my block will be moving up there. All right, so this is a typical conservation of energy problem. Notice all the stuff in the middle, all of this stuff here, it doesn't matter. So I could have said, oh, this distance from here to here is 25 meters, or there's, little hills like this. None of it mattered. All that matters is what's your initial state and what's your final state. So don't be fooled if you read the question and there's all sorts of information about the middle of this hill, or it goes up a 2-meter high hill and then an extra 1 meter above that. So if it did something like this, and you started here and you ended up here, but the fact that you went up and then up again, all you care about is what happened here and what happened here. So this problem is the same as this problem. You know, if this was 2 meters and then this was 1 meter, it's the same as going 3 meters all in one step. When you're doing conservation of energy, you're looking at 2 different parts of your system. An initial state, whatever you want your initial state to be, and the final state, whatever you want your final state to be. So here I chose the initial state is, of course, naturally, I've compressed my spring and I'm waiting to go. And my final state, I made where it is I'm trying to calculate. I'm trying to find the velocity up here, so that'll be my final state. So just be prepared to see, you know, if there's a question, and the question has something about the middle doesn't matter to you. Unless I say specifically, hey, this is location A and this is location B. How fast is it going at location A? And then how fast is it going at location B? Well, that's different. For that type of problem, you have to do this in 2 steps. You'll have a part A, conservation of energy, where the final state is over here at location A. And then you'll have a part B, where the final state is location B. Okay? But that's not this problem. This problem just said, you started over here, you ended over here, the middle stuff is immaterial to you. But anyway, you see that with all the practice problems that are posted. You know, I draw them a particular way, but that's just because it's easy to draw like that. I could have drawn the hills really steep, really shallow, bumpy. It really doesn't matter. What matters is your initial state and your final state. And that's why if you get into that type of thinking, these questions become very, very easy. So that's the kind of thing you should look for being able to do for conservation of energy type problems on the test. If you could do these types of practice, these examples that we went over in this, then you should be fairly good for the test because they're going to be very similar. You're going to work them the same way. The story may sound a little different. The numbers will be different. Maybe instead of sliding along a horizontal table, you're sliding on a vertical wall, or you're sliding along a ramp. Whatever the case, you're still solving it the same way. Which direction is motion? Get all the forces in that direction. Calculate the works. Once you know the work, set it equal to 1/2 mv squared, and you get your velocity. Conservation of energy, kinetic and potential initial is kinetic plus potential final. Ask yourself the questions about the initial state, ask about the final state, plug your numbers in, and you solve for what you want. So, hope you practice these problems. Of course, as always, if you have any questions before the test, please let me know, email me and all of that, and we can work through whatever issues you may have. But until then, good luck.